Good use of your time. All right.
Well, I was paying mostly attention to you.
Okay. Sure. All right. So let's talk about what we're doing today. We're finding derivatives still. That's the new unit, Unit 4, which is Chapter 3 for us. But we're going to get into very specific things. Why do certain derivatives turn out the way that they do? Explains why certain values turn out the way that they have. Today's goal is to continue on. This is something I brought up yesterday. We talked about sine. We talked about sine and cosine yesterday. We talked about how the derivative of that turns out the way that it does when you look at the picture. We're going to look at the same exact reasoning for these two. We're going to look at e to the x and tangent today. And then at the very end of tangent, we'll do an example of tangent where you have to do it by hand. Then what we're going to look at is we're going to go immediately into the Google question of the day. When I get to the Google question of the day, for the people that are online, you guys can log off at that point once we get there. And you can go answer it, and that'll be the last thing. I do grade the Google question yesterday, and I do grade it today. So make sure yesterday's you're typing in enough words I can understand how you're finding the derivatives. But let's jump right in. All right, let's talk about e to the x. All right, e to the x is my function.
So we're learning this stuff we already got tested over?
Yeah, because we go. Yeah, because we go. The next unit uses it still. We don't get rid of it.
Nice.
Yep, we just continue on. We learn new stuff with it. So, okay, here's the idea. E to the x, the derivative of it. We know the first derivative, y prime or dy dx, however you want to write that. Derivative with respect to x. The derivative is just e to the x. Accept that.
So that's the derivative of y prime. Oh, totally.
It looks like you just tried.
What?
Okay.
Derivative of y prime.
Well, you made something like 2 different things. You can't be a dog about it.
I'll get that.
Okay. All right. Hey, if you guys can't stay quiet, you're going to be moved. So, all right. So derivative of e to the x is just e to the x. Now, the real way we've done this, and this is something I didn't really talk about, e to the x is actually related to this function right here, which is a to the x function. That was the exponential. I just didn't discuss this. Somebody brought it up the other day. I just didn't go into detail about it. And so the a to the x, and that's not 9, that is an actual
That
a.
was me during the test.
Okay, good. Okay, I don't know. I forget. Well, I forget who did. So it was a good question. It's actually related. So when we did a to the x, the derivative is natural log of the base, right? Natural log of whatever that base number is, a or whatever digit it is, and then it's a to the x right after it. Okay, that's the first derivative of that function, right? So we use this fact to actually get this answer, believe it or not. I just never talked about it. We saved it for chapter 3 to explain why. The derivative of e to the x is actually the natural log of the base. The base e is actually a digit, right? E is like 2.7 something. It's a number. So you would actually put the natural log of that number, and then you just put the function behind it, right? E to the x, whatever the original item is. And then you also take it times the derivative of the power. Well, the derivative of x is 1, right? Because it's a chain rule. Well, here's the idea. Natural log of e, right? This actually stands for the log of base e of e. That's what that stands for. That's what the natural log means. It's log of the natural number. Well, what power do you put on an e to make e? 1. And so that thing right there, this turns out to be a 1 times e to the x times 1.
Or, I don't know what you just said.
This part right here, the natural log of e, this piece right here, is written like this when you write it out in like its full form. It's ln means log, right? But it's log of the natural number. So they already told you what your base number is. So it's e. That's what ln stands for. It's the natural log of that. Well, the idea is that how you solve logs, how you're supposed to do it in like pre-calc days. You're supposed to guess what power do you put on this number right here, this letter, to get this number right here. That's what a log stands for. It means what power. Well, what power do you put on e to make e?
1.
1. It's already an e, right? So you just put a 1. So that's what the answer of that part is. So when you take 1 times e to the x times 1, you just get e to the x. And that's why the derivative actually turns out to be itself. It's actually based on this rule. I just never discuss it because it's a colossal waste of time. It's one of those things like once you see it, you're like, okay, man, it makes sense. It's just, that's just the process for that what we go through. Now, if that a was any other number, you have to keep the natural log, whatever that number is. So
So the derivative of e
is e. Now, let's relate it to the drawings, because that's what we focused on yesterday. We looked at the drawings of like sine and cosine and proved that the derivative graph would be a certain thing. So let's take a look at this. What you're looking at here, this is the graph of e to the x. This is the full graph of it. Okay. So if I kind of zoom in here, you can see what e to the x is doing. It's starting off at 0, and then it's kind of floating its way up. That's the normal graph of it. Well, when we do the derivative, right, the derivative of this thing, what is the slope over here?
0, 1, 1.
Yeah, the derivative over there. This derivative right there, those are all zeros. These are horizontals. Those are all, the derivatives are flat. It's like horizontal lines. Then eventually, the slope starts to turn positive and gets taller and taller and taller and steeper and steeper and steeper. So that's the idea. So the slope actually is getting larger as we go. It's starting at 0 and going up and up. And so the idea when we actually draw the first derivative graph of this thing. So if I look back at this thing and I'm going to plot the derivatives and I draw just a generic graph. Well, my first derivatives were zeros. So my first derivatives were zeros, and then it started going positive after that, and they started getting bigger and bigger. Well, the derivative, when you look at the actual like graph, when you draw the first derivative, and this is the first derivative graph, it's the same graph. It's the same as the last graph, which is e to the x. When you actually find the derivative graph of this e to the x, it actually ends up being the same picture anyway. And it's really weird when you start to see it, and that explains why e to the x actually turns out to be e to the x. It's actually because of this graph as well.
Positive to negative.
What?
It's not changing from negative.
Exactly.
to positive.
Yeah, it just went from 0 to up, and that was it. So that's why the graph stayed the same when you did the first derivative. It didn't really go up and down. It's not oscillating up and down like sine and cosine did, where it's changing. This is just staying constant. So it explains why the first derivative graph stayed the same. But that was e to the x. Now, what I want to talk about next is tangent, and do the derivative of tangent. No. So now, if you don't know what tangent is, let me throw in a graph here. What?
Secant squared.
Yeah, we're going to get to that. That's the first derivative. We're going to get to that here in a second. And we're going to show that is the actual drawing of it. Question?
I thought it was 1 over cosine.
Which is the same as secant.
Oh.
Yeah, secant squared. Yep. So we'll get to that. That's something I'm going to write. You're right, and you're right. So let's get to that. So tangent.
That's about how
Most smarter version.
All right.
Yeah, Brayden.
Okay. All right.
No.
So let's take a look at one drawing of this. Now I'm going to zoom in so you can see this. One drawing of tangent. It has a frequency length of pi. So we split half of it over here, half it over here. So this is pi over 2 and negative pi over 2. That's the first derivative graph. Let's see, did I start my camera? Let's see. Yes, it did. Good. All right. And so we have half over there, half over there. We split this in half again. So this is negative pi over 4, negative pi over 4. And then it goes up to 1 and negative 1. And the idea is that tangent has asymptotes on the outside. And then the tangent graph itself starts in the upper right corner, flows down to the first marker, flows down to 0, goes down to the next marker, and goes off to negative infinity. This is a normal graph of tangent. They're all broken up, right?
Now that I follow.
Okay, that's what we've done previously. That's what you're seeing here. Whoa. That's what you're seeing right here with this graph. It's going out to those numbers. It's just repeating. I didn't have one picture length here. I have like a ton. But when we draw the first derivative of this thing, we look at the graphs of the derivatives. Well, the graph right here, the slope is positive. It stays positive, and it never ends up ever turning negative or 0. It got closer to 0 in this region, but it never actually went to 0. It actually probably, more or less, it looked like it actually ended up being a slope of 1 right there, and then it went back up to positive again. but it was getting smaller. The slope actually got smaller until it went larger again. But it was positive the entire time. So when we draw a picture of tangent's graph, I forgot to put a blank space in there, sorry. All right, when we draw a picture of tangent's graph of the first,
It's gonna be a parabola?
the first derivative, yeah. The idea is that
Well, yeah,
the
I saw that on the next.
yeah. So the yeah, good point. I mean, let's
So smart trap.
I know.
let's get rid of that. Sorry. All right. Okay. So we draw this first derivative graph. The idea is that the slope was positive, and it was getting closer and closer to zero until it stopped, and then it started going positive again, and it never actually reached zero. So it actually looks like a parabola when you looked at the first derivative of tangent. We saw the slope was always positive. It never went down to negative numbers. So it never went below the x-axis. This is what the first derivative of tangent looks like, which is this graph. This is what it looks like. I just repeated it over and over because it would just keep repeating with every picture, right? And as you can see, it's hitting 1. The slope actually ended up being 1 at the middle, and it went up to positive. Well, here's the thing, and this is what Morgan brought up, and this is what I heard as well. This is actually just 1 over cosine squared's graph. It is actually 1 over cosine squared. I typed that in decimals, and they lined up perfectly on top of each other. And so it's actually the exact same looking picture. It's one of those things, like once you see that concept, it makes sense why the derivative turns out the way that they did. It's the same with, and this is my last slide. This is the absolute last slide of the day. 1 over cosine squared. This is the first derivative of tangent.
See, I hated that.
What?
The way you drew the CO.
Oh, sorry.
It's okay.
All right. So, okay. Okay, so here's the idea. So tangents, so the derivative of tangent is 1 over cosine squared, which this is a 1 over cosine. This is just written differently. This thing is the same thing as secant. 1 over cosine on your property sheets, if you remember back to calc days, or pre-calc I should say, it was 1 over cosine is the same as secant, and then the power of 2 can go on the inside, and you can write it with the power, because this is the definition of an exponent. You can write it like this. These are the same thing. I'm going to highlight these. The derivative of tangent is 1 over cosine, or it's the same as secant squared. They're the same thing in form. Now, when we do it by hand, when you have to actually take a derivative of tangent, let's say we're going to do like 5 tangent of 2x. If this is my function, and I want to take a derivative of it, no matter what, it's still a chain rule. You still do chain rules. So the derivative of tangent is 1 over cosine squared of that same variable, whatever that variable is for tangent. Notice I just left the 5 out front. The 5 didn't really matter, didn't affect anything. So it's derivative of tangent is 1 over cosine, and then you have to take it times the derivative of the inside. Well, what's the derivative of the inside of with that parenthesis? 2. And so the overall answer on this problem, it ends up being, with the 5 and the 2 both multiply to the top, that's how you multiply whole numbers on fractions. So 5 times 1 times 2 on the top ends up being 10 over, ends up being 1 over cosine squared of 2x. That's the answer. Or this.
Yeah, I like that a lot better.
Yeah, without fractions. It's just the derivative tangent is secant squared of whatever the variable is. You still do the same work. The 2 is on the, we jumped the 2 on the outside because we took the derivative of the 2x as well. So it still ended up being the same answer. It's written differently, just so you can see that. Questions? Okay, that's my last slide of the day. The Google question of the day, I give you a tangent, and I want you to find the first derivative of it. And you just type it in. You can type it in like the fraction, or you can type it in with secant squared. In fact, it actually might be the one you're looking at, so go look at it. It might be really close to this.
Keep that up there for a
Okay,
second.
I'm not. So, write it down really quick. This is about to go away.
10 secant squared 2x. Got it.
It might actually be the same thing. Go look. I don't know if I typed in 5 or 2.